Hello, I'm David Barbera, and I will present our paper, An Utterance Verification System for Word Naming Therapy in Aphasia. Aphasia is an acquired language disorder, most commonly caused by stroke. Anomia or word-finding difficulties is the most common symptom in aphasia. In normal times, therapy provided by healthcare service would be from 8 to 12 hours. However, proven dosage to see improvement requires at least 100 hours. The current pandemic has made matters worse for patients who travel and visit speech and language therapists. Around 350,000 people in the UK live with chronic aphasia. Anomia is tested by picture name test. Picture naming task is a type of intervention where the speech and language therapist presents pictures or drawings of items and the patient has to name them. There is a limit to the number of hours a therapist can dedicate to a patient and the number of patients they can reach to provide this type of intervention. Digital means, as in the form of mobile devices like tablets or phones, would allow patients access to more hours of practice but independently, reducing the number of visits to the therapist, which can be reserved for more complex interventions. However, to make it possible, we require reliable automatic assessment of naming attempts for people with aphasia. To formalize this challenge for an automatic system, we could define the problem as to verify that a certain word that we know beforehand is uttered in a given segment of speech. To create a system, what we have explored is comparing posterograms from a speech with dynamic time warping. This approach has been used before by Anli using Gaussian mixture models and also deep belief networks to generate posterograms from a speech to compare utterances from L2 students of a language to a native speaker. What we propose is to use deep recurrent neural networks to generate phone-based posterograms, which could be more sensitive to detect bizarre phonetic combinations that tend to be common in aphasic speech, and use them to compare aphasic utterances to those from a healthy native speaker. To generate phone-based posterograms, we require models trained on corpora with phone alignments. We use SJCam0 for this purpose. Using those alignments, our models can learn to transform speech into a sequence of phonemes to a reasonable degree. However, what we are interested is in the posterior probabilities of those phonemes for each speech frame we apply our model. Those are the phone-based posterograms. Just quickly, to understand how posterograms can be compared, what is usually done is to compute all possible distances between pairs of posterograms using the minus logarithm of the inner product of them, which gives us a distance matrix, here visualized in colors, where dark blue represents distances close to zero, and any other higher distance can grow up to dark red, as represented by the color in this graphic. Then we can use the dynamic time warping algorithm to search for the path that minimizes the accumulated distance, which gives us a distance measure. The idea would be for this distance measure calculated on phone-based posterograms to give us a way to discriminate pronunciations that are similar but not the same. For example, for the word tree uttered by a healthy speaker, when compared to an aphasic speaker to pronounce the word tree correctly, would give us a low distance measure, and when compared to a pronunciation that changes just one phoneme like tra, would give us a high distance measure. The pipeline that we use to transform speech into phone-based posterograms is as follows. We fragment the speech signal into frames of 30 milliseconds of speech every 10 milliseconds. Then we extract from each frame a vector of 26 acoustic features, 30 mil frequency capsule coefficients, energy, and their corresponding deltas. Then we apply to such vector our best performing model trained on SJCam0, which consisted in a 7-layer deep bidirectional gated recurrent neural network. And finally, with that, we obtain a vector of posterior probabilities, or posterogram. We choose to assemble all these ideas into a working system the following way. Incoming speech is processed by our deep recurrent neural network to obtain the posterograms. And then using posterograms obtained offline from the speech of two healthy speakers pronouncing the target word, we make a comparison using the dynamic time warping algorithm, resulting in two distant measures. We use the minimum of those distance measures to calculate if it's bigger or smaller than a pre-calculated threshold fixed beforehand, to make a decision if the word, it's 3 in this exemplar, has been pronounced correctly or not. How we decide which threshold to use to make the final decision. We try two ways. Using previous naming attempts from a group of patients, we choose the threshold that gives the best performance, and then leave it fixed for any other new patient. We call it the fixed version of our system. Another way we explore is to calculate the best performing threshold for each patient. Here the assumption is that we will have previous data from the patient in the form of labeled naming attempts, probably from an assessment of a speech and language therapist. We call this one the adapted version of our system. To test our system, we collected data from 8 chronic post-stroke phasic patients, tested them on 220 items, which resulted in a total of 1,760 naming attempts. This is the demographic and clinical data from the patients. We conducted an early assessment using the object naming and repetition test from the comprehensive aphasia test battery to record their level of impairment. Here is the final scoring from the speech and language therapists engaged in this study. From all the naming attempts, the therapists scored online while patients were being recorded without giving any feedback. Note here patients 3 and 5 had the lowest percentage of correct attempts. Later on, we invited the second speech and language therapist to score the naming attempts offline to have an idea how therapists could disagree in their assessments. Overall, a coherence kappa of 0.92 shows an almost perfect level of agreement. Lowest kappa per patient was 0.84, which still shows a strong level of agreement, and highest 0.99, which is a perfect level of agreement. Since there are no existing baselines that we could use to compare the performance of our system, we decided to use off-the-shelf standard speech recognition service. The rationale in doing so is that it would be the fastest way for a clinical lab to get automatic digital therapy up and running. We use Google Cloud Platform, speech-to-text service, and adapted it for our task. Since the service provides transcriptions, what we did was to check if the target word was in the transcription. If it was, then the naming attempt was considered correct. Otherwise, would be considered incorrect. In the end, the results show that overall, in ideal conditions, the fixed and adapted version of our system performed significantly better than the baseline. However, didn't reach comparable performance to the scoring of the second speech and language therapies, whose performance is here calculated in terms of our main speech and language therapists who conducted the assessments online. Per patient, the worst performance of the fixed and adapted versions of our system happened on patients 3 and 5, which had the lowest scoring on the object naming test. However, for patient 6, the performance was comparable to that of the second therapist used in this study to score the attempts offline. In general, fixed and adapted versions performed better than the baseline, except for patient 4 and just for the fixed version for patients 2 and 5. To understand how the performance of our system could generalize to unseen data, we use tenfold cross-validation. Results show that performance remained high. A wide range of F1 score and Matthews correlation coefficient shows, though, that for some patients, the system will be not as reliable, and that actually happens as well for the baseline. To summarize the results, performance of our proposed system reached accuracies above 83.6% with an average of 89.5%, which is high. Overall, our system was significantly better than the commercial baseline for both versions of our system, and per patient, significantly better for patient 6, 7, and 8. Remarkably, for patient 6, our system reached a comparable performance to that of a speech and language therapist. Our immediate next step is to use our current prototype to gather large amounts of naming attempts within the context of a comprehensive clinical trial, which is meant to test iTalk, a gamified intervention app that automates the assessment of picture naming tasks. Future work will be dedicated to analyze the effects of live feedback on patients and to adapt the current prototype to work offline on already gathered recordings of naming attempts. Also, it would be very interesting to investigate if our system could be used effectively in other languages without the need of even retraining our model, which are based in English. Thank you for your attention.